Sorry. Hi. I guess I should start now because of someone is taking care of the system, so I have to lay a little bit. So just a announcement make first is tomorrow we start our optional tutorial which covered R and Python. I think R is covered in the first few weeks, and I think the TA will be going over that later view on this part. So what we are going to do today is to quickly finish this Excel part, and then we will go to the next part. So usually I would assign homework when we finish one topic, but the fact that other section has missed two class, so that's why I would delay send out the assignment until the other section has finished its material. Probably next week I will give out the assignment. Okay, so let us quickly go back to the Excel. So just to remind you what we have been working on so far in Excel, right? Is we learn just quickly go back to the beginning. Okay. Maybe I use that mic. This mic is not very good. Can you hear me? Okay, good. So so quickly the Excel, we can use a calculator, and we learn the standard operation, square, exponential, count, sum, run up and run down, and then we learn the mean is known as average. Okay, and weighted mean we require product sum over sum, and median, there's a function called median, and mode we have a function called mode dot single, and the range we rely on the max minus mean. Okay, and for IQR we can use the quantile exclude 3 minus quantile exclude 1. Okay, and then for variance, there are two types. One is called variance.P and variance.S. Okay, one is divided by n, the other by n minus 1. Okay, and the sample and population version of SD. Okay, and for coefficient of variation, and we don't have that, but you just divide it by the mean. And I think last time we talked about skewness and kurtosis, right? The SKEW.P is a population skewness, and the one without P is the sample. There's no dot X. And then this is sample excess kurtosis. Okay, you can check all these inputs should be consistent with what you find from your slides. Okay, so this is all the calculation here. This I skip. Okay. So what remain we want to show you is several things. Is the scatter plot, how to do covariance correlation, and then we'll work on some add-on package. Okay, so that will be the three things that I want to talk about Excel. Then we go to immediately go to the probability. Okay, so in this slide it actually summarizes all the thing that we discussed. So this is a good slide to summarize if you want to go back to see what are the formulas. Okay, so on top of scatter plot, okay, So I would open Excel, I guess. Okay. Again, I'll just magnify that. Okay. So I think I put X and Y here. Okay. And what I'm going to do is to just put in some number here. Okay. And what I want first thing to do is to draw a scatter plot, right? So what we're going to do is to highlight two columns. Okay, use the mouse, or you drag over the cells. Okay, that will be fine. And go to insert. And good thing is scatter plot already is in the recommended chart type here. So you get check scatter plot. Then immediately you can see is there already. Okay, so here is already the easiest way to construct the scatter plot. Okay, so let me put to the side. This is a scatter plot. Okay, so very simple. I don't think I need further discussion on this. So what I want to show is the following thing. I want to show several measures. First is the covariance. Okay. The population version and the covariance .S. Okay. So this is the thing I want to show. There's two calculations here. Okay. So it will be covariance.P, and then you have to input two set of data. So first thing, you highlight the first set. Okay. A2 to, and then the next set is B2 to B6. Okay. So that would be the way you would do if .P with population. Okay. So in case you would not fully follow, I use formula text here. So this is the covariance. Okay. And I also can do the sample version, covariance.S. Okay. Again, I would want to tell him what the data I have is A2 up to A6, comma, B2 colon B6. Okay. So this would be the one we see, and that's what we expect, because the sample version would be larger than the population version, because the population version is divided by n, and the sample version is divided by n-1. Right? So that would be the formula. Okay. And is that okay? The last thing I want to show is correlation. Okay. And we know correlation do not have anything related to population or sample, right? There's only one single formula. That would be very simple. Would be just CORREL. Okay. Again, is A2 up to A6, comma, B2 up to B6. Okay. So that gives you almost 0.7 correlation coefficient. Okay. So here I want to, because of Excel, I want to try to verify the two formula. Okay. I want to try to confirm the two formula here. I want to use the population covariance and population standard deviation, okay, to confirm the formula I have. Okay. So what I'm going to do is I use the covariance P of this, okay, and this part, right, as the numerator. Okay. And I want to divide the standard deviation population version for the X. Okay. multiplied by the standard deviation population version for the column Y. Okay. So just to remind you what I'm doing here is I use the formula to calculate correlation coefficient, where the numerator is covariance and denominator is product of the standard deviation, okay, of the two input, right? So you can see how to here. If I have population, I do population here, okay? So that is the same formula as you can see, okay? And you should expect we should have the same formula when I replace everything from P to S, okay? So what I'm going to do is I copy this formula here, okay? And I place here, but instead of P, I have everything replaced by the sample version to convince you that no matter you use the sample version of population, I'll give the same result, okay? So this justify why for correlation coefficient, we don't have the population version, right? Or sample version, they're the same. Is there any question? Also, any question from the any question from the I don't know, from the Zoom? Is that okay? Because I can't see any of you. I mean, okay. Is there any question for the correlation coefficient? Okay. So now, if there's no question, then basically you know how to handle statistics in Excel. Basically, if I ask you anything from the class, okay, you don't need to start. You can do the calculation from Excel and do it without using the pencil and paper or calculator, okay? Excel can do everything for what we need to do, okay? When you do your project, then basically you can use Excel. Of course, you can use R, which you will learn in the optional tutorial on tomorrow, okay? Tomorrow at evening, then there will be optional tutorial. So lastly here, I want to show you one thing is Excel by itself is not powerful enough to do a lot of things we want to do. So that is that's why Excel we have something we call Addin. Okay, you can just imagine that like a smartphone, right? It has some basic function. You can download some app to improve its functions. Okay, so the same idea here is not sure if it also applying to your iPad as well, but what we need is we need to have some new function here. I'm not sure the iPad has, but I need to show you. So here, what we're going to do is go to File. If you have this, have your computer, you go to Option here, and then called Add-ins. Okay, I'm not sure we can do it because you rely on a C library. Whether I don't know whether it works in your system. Okay. So here you can see there are many things here that are a lot of add-in. In particular, we will be using one add-in, which is the first one, which we call the Analyst 2-pack add-in. Okay. So this one would be the most important thing we need to do. So we need to input here because not there yet. So what we're going to do is we want to make it active. So just to go back to how to get to this page is File, Option, Add-in. Okay, File, Option, and so here, File, and then Option, and then you can't fully follow. Okay, and then here go to the goal. Okay, and here you can see there are 4 choices. Okay, and for our purpose, we will need the first one. Okay, if you learn linear algebra or other finance class later, you might also need the last one, the solution, the solver, but the first one will be enough, okay? And that's something we need, okay? So NS2 pack. Okay. Here, once we do it, you can see immediately we have something here, okay? This is something in extra, okay? Once you add that thing, okay? Let me do it again to make sure that everyone knows what I'm doing. So go to File, Option, okay? Add in, Go, okay? And there's something called NS2 pack. Then you have to make sure that there's a tick here. Okay, just try to click, unclick until you get it. Okay, is that okay? Okay. So don't worry, once you activate it, you will see there's an analyst here. Okay, in the data analysis. Okay, this one once you're done, then everything become a dummy thing. Okay, just click and then you're done. Okay. So let me show you how this thing can be done. Of course, it's already in here. Okay. So as I said here, they go to the option, add in, right? And you will see NS data analysis. Okay. So the first thing we want to do is what we call descriptive statistics. Okay. So let's do the following. I create a new worksheet. Okay. What I'm going to do is I try to maybe start from X, right? I just need one single thing here. Okay. I just randomly create some number. Okay. Okay. I just random some number. Okay. So the first question is, okay, we want to know a lot of things, right? We want to know mean, median, mode, variance, that's a dispersion, IQR, all those things, skewness, dispersion. Okay. Is there any way Excel can generate this for us automatically? Okay. Because of course we can do it easily, right? We know how to do it, right? The answer is yes. Okay. That is what we call go to data analysis. Okay. Go to data analysis, you click it. So data at the end, data analysis. Okay. And then you click descriptive statistics. Okay. Go to data. Here. Data. Okay. And then you go to data analysis. Okay. And then you choose descriptive statistics. Okay. Okay. There are many things you can choose from, but we'll talk about descriptive statistics, correlation, and covariance. The three things we discuss. Okay. But let's focus on this one first. Descriptive statistics. Okay. Exactly the topic we are having right now. So first, you can go click in here. You can see a something to input. Okay. So let's make our life easy. Okay. What we're going to do is we need to tell them what is the input of the data. Okay. So here actually the data is by column. Okay. So here I can say, tell them I click this one. Okay. I click the whole column. Okay. And I only have one column. The data is by column, so it is column. If the data is by row, then by row, that this is column. And the second thing asking whether you have label in the first row. Indeed, I have X is my first row is label. Okay, I do. If you don't have label, then you don't have label. And the next thing is you want to tell them where to output your result. Usually, I want to output it within the same thing. So I usually put, say, I put here C1. Okay, doesn't really matter which one you're doing to do. And we want the summary statistic. That's what we want. Okay. So then we say okay. Okay. Once you tell them the input, tell them the details where the output. You click some statistics and you click OK. Okay. Then you will see very nicely, it gives you the mean, the SD, the mean, the mode, okay, the sample variance, kurtosis, skewness, range, maximum, minimum. You don't have IQR, but that is you can do it quickly. Okay, so to let you see how convenient is, I just add another data set. You can do multiple data sets at the same time. Maybe I have 1, 3, 6. Okay, so suppose like this. Okay, if I want to do this at the same time, I can do that. There's no issue. Okay, so let's see. I do it again. Okay, to show you how fast this is. Data analysis. Okay, and I choose descriptive statistics. Okay, and now the only difference is the data I have is I have X and Y, right? I have 2 columns. So I will tell them I have 2 columns here. Just highlight the 2 columns. Okay, it's $A, comma $B. Okay, just the whole column, and then I can just choose the same location. Okay, just override. That's fine. Okay, you can easily see that. Okay, quickly, Excel will output most of the thing you want. Okay, so that is how Excel use Addin to do things. Okay, and is that okay? Okay, so the next thing I want to show quickly is to show you the other 2 functions here, which is called correlation and covariance. Okay, and to do so, I have let me open another spreadsheet. Okay, because I want to have correlation, coefficient, and covariance. I want it to be balanced, so I just take away this 2 things. Okay, just left this. Okay, make it the same observation for X and Y. So now I want to do covariance and correlation. Okay, so I'm going to do is I first do covariance. So I choose covariance. Okay, choose covariance. Okay, do the same at the input range. Okay, I click both A and B. Okay, and then the data are organized by row, so that's why I choose column. Okay, and I've labeled in the first row. Okay, and I tell them where I do the output. Okay, I choose say D1. Okay, okay, so this is the case, and then just click OK. Then automatically you have covariance. Okay, don't worry, I do once more for the correlation. Same thing here. Okay, let me do one more correlation. Okay, the same thing because exactly the same procedure. I choose correlation. I choose what's the input, which is 2 columns here. Okay, and my data is organized by column. Okay, and I have label in the first row, and then I choose the output range. Maybe I choose D5 here, and that gives me the correlation. Okay, so that is the end of the Excel. I'll go around to see any problem. Okay, if not, then we end this topic 1. Okay, because this is a standard thing. You know, Addin, you know how to handle Excel, right? Basically, so possibly, if you're brave enough, start to add 1 line in your CV that you know Excel. Okay, but I go around to see if any question, or if anything, then you can just tell me. I don't know whether iPad can work on it, but if not, then at least you know what's going on. I think the slides in the give you enough detail that you know how to do. Okay, I think it should not be an issue, but I just go around in case you have any question. Some of you raised a very good question. When I calculate covariance, you can see there's free entry here, right? So you ask, what is this guy? This guy is actually the variance, okay, of X. So let's show you. I do the variance P of X. So, okay, if I do variance P of the Y, just give you this guy. Okay, so so that is how okay. So if you use math, then probably you still have this function. Like Someone asked me, what is exactly this guy? This guy is exactly covariance because that is the covariance thing. So let me show you. So covariance P, I got X and I got Y. Okay. So let's go ahead. Covariance are two columns. Okay. So that's how you get this number. Or sometimes you want to know how I get what is it, the covariance. Okay. And just to remind you one thing, some of you asked me why we look at the correlation, what's different between correlation coefficient or covariance. The answer is correlation coefficient normalize everything between -1 to 1. Okay, 1 is on a straight line, positive straight line, -1 is negative straight line, right? So and then you can say when you're closer to 1, they are more positive related, right? And as respect to covariance, you don't know because it can affect by measurement unit, right? When you calculate things by 10,000 or 100,000, then the covariance would adjust, right? Based on your measurement unit, okay? In order to compare two different data set, right? So that's why you would go for the correlation coefficient. That's like when you try to compare two data sets, when you try to compare their dispersion, you would use the CV, right? Correlation of variation, right? Coefficient of variation, right? You divide it by the mean. Or that's why the kurtosis or skewness, you would divide it by the SD, right? Because you want to normalize it in order to not be affected by measurement unit. Okay, is that okay? So that's why kurtosis, skewness are all unitness. Same as correlation coefficient is also unitness, right? There's no unit. Is that clear? Any more question? As I said, the assignment are supposed to give now, but because of other section have missed it 2 class, so I will wait until they're done and I give the assignment. The assignment I would say is very simple, the first one, so don't worry. You shouldn't take more than an hour to do it. I mean, it should be half an hour, should be done. But anyway, I will wait until this one I would put it in the blackboard during the break. Okay, so let me save it first. I put in the blackboard during the break. Okay, if there's no question, any question for the Excel? Okay, so if no, then we then talk about probability. Okay, let me quickly talk about probability before the break. Okay, so I think we only have 10 to 15 minutes before break. Okay, there's no question from the Zoom. Okay, do you record the lesson? I think so. If you ask, you can just email me if you want. I don't know how to do that. So probability, okay. So as we are done with statistics, okay, we would go to probability, okay. The question, I reiterate again why we need probability is because of we are never able to have all the information that we want, okay, and we have to rely on sample, okay. When we have to rely on sampling, we have something called unknown, right? Because we don't know what's going on for the thing we do not see. So that's why we have to rely on probability, okay? So to start probability, we have to define what is probability first, okay? And we will start from defining probability based on the classical definition, or what we call the frequency list definition, which we will soon see is the long-run frequency. But before we do it, we have to define what we call random experiment, because the classical definition of probability requires things that we can repeat a lot of time, and from a lot of experiment, from the data, then we generalize the idea, and then we get the ideal probability, okay? So let's start what we call random experiment, okay? The idea of random experiment, we don't define formally, but we can describe what it is. A random experiment is refer to something that is going to occur, okay? We know what are the possibility, what might happen, but we don't know which one, right? Because if we know, then it's no longer random, right? That's why random experiment is something random may come out. And we are talking about a random experiment must be able to repeat itself many times, okay? If not, then it's not usually not meaningful in classical sense of random experiment, okay? If things just happen once and not going to happen again, then random experiment is not really useful, right? And for example, we toss a coin, roll a die. These things, you know what the outcome, right? Toss a coin and maybe head or tail, one of the two sides. Roll a die must be from the outcome must be, the possibility must be 1 to 6, right? There's no other way around. And you can potentially repeat this many, many times, okay? And then we can talk about probability, okay? And formally speaking, an outcome is a possibility of the random experiment, right? And as I said, toss a coin, no head or tail, okay? And in the classical definition, we can group different outcome, okay? And we will call event, right? For rolling a die, we will call even numbers an event because it grouping all the outcome of 2, 4, and 6, okay? And the sample space means it contains all possible outcome, okay? And itself is an event, right? Because it's grouping of outcome, it's grouping everything possible, okay? So tossing a coin, the sample space is head or tail. Rolling a die will be the sample space is 1, 2, 3, 4, 5, 6, okay? So here, do note that we have some implicit definition when we have all this terminology, right? We call random experiment, outcome, event, sample space. The fact that we know the sample space means that there will be no surprise with respect to the outcome of the random experiment, okay? It must be the case head or tail. It must be the case 1, 2, 3, 4, 5, 6, okay? We can't have a case whether we come out with a die at 7, okay? We cannot toss a coin and the coin disappear, okay? That's a magic, right? But we are not talking about magic, okay? We have to have the must be head or tail, okay? Okay, it can't be other way around, okay? You can't not have head or tail, you toss a coin and a rabbit, okay? That's not allowed, okay? If you want to allow rabbit, okay, you must, when you specify the random experiment, it must be head, tail, or rapid, or disappear. Okay, you must allow that. Okay, there are no surprise in terms of outcome. Okay, now once we have this, we will have the definition that we have been using a lot of time, what we call the classical definition, or what we call frequency list probability. Okay, the idea is that if we are to repeat random experiment many times, okay, in that case, we have a data, right? And then we can count the frequency, how many of them of the head, how many of them of the tail, okay? And the ratio, okay, what we define the fraction is number of outcome that favorable event over the number of time experiment you can conduct. That is what we define as probability. Okay, so that's definition. By this definition, actually it's very natural and turn out to be from real world. We know this number going to be stable. Okay, because we toss a coin, the fair coin, it's very likely that half of them, we told million times, right? The fair half, around 500,000 is head, 500,000 a tail. Okay, so that's why we would say the probability you get a head is 1/2. Probability get tail is 1/2. Right? So that would be the idea of probability. Okay. So just to remind you that the probability here, we have to emphasize that it's related to random experiment. Okay. Potential can repeat many times. If you can't repeat many times, then the probability you get usually is not that meaningful, right? If just achieve once and for all, then the probability is not the probability we meant. What do you mean by that? Okay, all of you are in Hong Kong, and I suppose you would know what do you mean by typhoon, right? A tropical cyclone. And in that case, we will even over the time we say the observatory, we said the typhoon would hit Hong Kong with probability of say 30%, 60%, 80%. Okay, what does that mean? Okay, well, the typhoon is not going to hit Hong Kong many times, right? What is the meaning of this in this classical probability? Okay, the fact that is what the observer said is the typhoon will hit Hong Kong with certain probability is not the probability we mean by here. Okay, because we're not going to say, okay, let's click the play button. Let's see whether the typhoon hit Hong Kong. Okay, we run it 1 million times to see 30% of time it hit Hong Kong, 30% of time doesn't hit Hong Kong. Then we can say from free. No, they didn't do this. Okay, what they say 30% is trying what we call the subjective probability or expert evaluation. It's not random experiment. Okay, and of course, what they are thinking about 30% in their mind is what we call simulation, right? They run a mathematical model and try to change some variable, and they run million times of that random variable, and 30% of that simulation lead to hitting Hong Kong, otherwise not. So it's still a kind of frequency idea, but the random experiment is not the real experiment. It's in their mind, they want a computer experiment. Okay, but it's related to this, but it's just a judgment, right? And sometimes they said, the expert would say, what's the probability that next year with earthquake, right? These are all some judgment, okay? Or subjective, what we call subjective probability, okay? This related to your belief, right? Just like ask a question, how likely that if you tomorrow you try to buy a lottery, how likely that you win a lottery, right? And those things are just involve some judgment, right? Or the question would be the following: you are saying that the probability that suppose last night I go to the fridge, and I figure out that moon cake or a cake has been eaten, okay? And I try to go back and say, okay, is it going to be the job done by my son or my daughter? Okay, without any judgment, I would say half likely be my son, half my daughter, right? But in the real world, right? Suppose the cake is very small, okay? It can only be eaten by one guy, right? Either my son or my daughter eat it, right? Or maybe a mouse, but anyway, just assume that only the human can open the fridge, right? And in that case, there's no probability, right? It's only the son or daughter, okay? In the classical sense, right? Because there's no uncertainty here. It's either you just don't know. There's no uncertainty, okay? So you have to distinguish the idea, the probability in this way, right? Something happened, you may still assign probability, but that's just reflecting what you believe in, okay? So that's why I said the probability can be a little bit tricky in the real world use, right? The probability can say reflecting your subjective belief, right? Because you don't know, I don't know whether my son or daughter who eat the cake, right? So it's half likely. Or some judgment, right? Next year, is it very likely to have earthquake? Some future prediction, also I can use belief, okay? Or the typhoon idea, right? It's not real random experiment, but experiment by computers computing, okay? And today we talk about the classical probabilities. We consider random experiment. Something can repeat and usually get repeated. And then because of this, if you do this experiment many times, then it tends to be stable thing. It's a ratio. So this is a well-defined concept. It's a relative frequency, okay? Okay. I guess I should stop here for the break. And then we will go ahead from the next, we'll talk about more stuff. Okay, so let's a break. We'll resume at 5:30. Go around to see if any question. Hi. Any question from the Zoom? No? Okay. So now we just to recap what we learned before the break is that probability we define as a classical sense is we need to have random experiment that potential can repeat many times, and the probability we set is in fact a long run frequency. Okay, that is definition. Okay, so this is what you learn in your high school. Okay, so now the good thing is, remember there are many things we can call probability, right? Just like expert judgment, we can do computer simulation, we can do our belief, right? What we think. Okay, so can we extend our idea? Yes, we can. Okay, so that is from now on, we will drop the idea of what we call the classical definition. We will start recall from the axioms. Okay, but later we talk about that. But before we go ahead, let's talk about the classical ideas first. Rolling a fair die. Okay, 1 is an outcome. 2, 3, 4, 5, 6 are outcomes. That's natural. And because the die have 6 faces, then sample space is everything there. Okay. In terms of math, we use the curly bracket to represent a set. Okay, a collection of stuff. And even number is an event, odd number event, large number event. Okay, you can imagine a small number, which is 1 to 3 is also event, right? Or anything is also event, right? 1 and 2 is an event as well. Okay. And the probability of even, odd, and large, okay, it just because it is a fair dice, okay. That means that each number would appear the same number if you keep rolling it, okay. So that's why just you will see 30%. I mean, there are 6 possible outcomes, right? Then you'll be 3 of them are the same, right? So 1/2 equally likely that we'll see them. Okay, so that is the idea of classical probability. Okay, and if you try to draw it, we call the Venn diagram. That's called a Venn diagram. Is you can represent the outside, the rectangle, the yellow rectangle, the sample space. Okay, and this green O is the odd number, L is a large, E is even, right? So you can see this how you can draw this, and later you will see we'll go back to this later. Okay, but this is what we call the Venn diagram. It's very useful if you want to do more statistics. Okay. So let us consider things more than a roll a die. You roll a die twice. Okay. And if you want to describe the outcome, then it can be represented by a pair of number, right? The first entry is the first die, the second entry is second die. Okay. And do note that when you have 1, 2, and 2, 1 are different, right? So that's why sometimes we call order the pair, right? The pair, the order mean things. Okay. And you may say, okay, I may not care about the order. Okay. Sometimes we don't, right? So that means that we are going to simplify the sample space. Okay. In that case, we require something we learn the next topic we call random variable. It tries to simplify the sample space. But anyway, for the moment, we don't. We just keep everything there. Okay. The sample space you can see will consist of all possible order pair. Okay. And you will have 36 outcome, right? Because it's the first entry, you have 6 possible outcome. The second entry, you have 6, right? And you try to draw a table, right? 6 times 6, right? So 36 outcome. Okay. The question like event, the sum of 2 die will less than 4. Okay. What are the outcome there will be 1, 1, 1, 2, and 2, 1. Okay. When you other than that, you have more than 4. Okay. So because every single outcome is equally likely, right? In this framework. So the probability will be 3 over 36, right? Which is 1 over 12. So that is the classical way to do things. Okay. Is that okay? I think that shouldn't be difficult. But is there any question? Okay. If no, then we need to, unfortunately, need to introduce some kind of set operation or operational event. And then later we will talk about some special thing. And after that, at the end, we will start from the axiomatic definition of probability. Okay. Why we need to learn that later is because we don't want to talk about random experiment. We want to define probability just based on math. Okay. And then in that case, you apply whatever interpretation you want. Okay. But let's go back to the beginning now. We want to talk about all this. Okay. And I'm sure you would find it boring. Okay. I'm also sure that you would find not very useful because once we know the probability, the same definition, but we need to know what's probability, right? Because that's why we have to learn this. But it's boring, but still it's very intuitive. So don't worry. So because event is so central to probability, right? Because we always assign probability to event, already know how to combine event, right? Or some operation. So we call intersect, union, and complement. So let's start with the intersection. Okay. Intersection is an event that contains all common outcome in A and B. Okay. Looks complicated, but it's very simple. Look at example. Okay. Just roll a die. Okay. The outcome you can have is 1 up to 6. Okay. You have even event, odd event, or large event. Okay. Look at the common element between E and L. Okay. That is the intercept L. 4 and 6 appear in both event, then it's 4 and 6. Okay. That is actually same as when you learn from your high school. It's called finding common factor. Right? Find a common thing there. Okay. For O and L, the common factor is 5. Okay. So immediately ask yourself, what is E intercept O? What's that? You'll be nothing because there's no common element. Okay. E and O will be nothing. Okay. So if you try to look at it, you can draw a Venn diagram. E will be 2, 4, and 6. L will be 4, 5, and 6. And the area, the overlap is called intersection, right? So that is why we have a good to have a Venn diagram being drawn, right? Or I go back to the original here, you can see 4 and 6 is become a purple color because they overlap, right? So this intersection is the overlapping area in the Venn diagram, okay? Is when they have common, okay, intersect. Now, the next operation, what we call is called union, okay? Union means join together, means that contain all elements in both A and B, okay? Is to get everything there, okay? So go back to the example, we have roll a die, even event, odd event, and large event, okay? What is E union L, okay? Just to pick up every element in both E and L, okay? Do note that because of set, okay? So 2, 4, and 6, 4, 5, and 6, you can just 2, 4, 5, 6, okay? You have 2, 2, 4, 4, 5, 6, plus if the element repeat itself, doesn't have no difference, okay? What I mean is if you try to write 2, 2, 4, 5, 6, okay? The same, okay? Because if things repeat itself has no, appear twice has no meaning, okay, for a set. So that's why basically you write everything, take out the duplication, that's why you have union, right? Because include everything. So you just combine, concatenate or join them together and take out the duplicated part, right? And O and L will be 1, 3, 4, 5, 6, okay? Ask yourself, what is E union O? E union O will be just S, because we have everything 1, 2, 3, 4, 5, even and odd must be everything there. Okay, is that okay? So it's a union. Okay, and if you want to use English, union is just an English word or. Okay, and for the intersect is the English word and. Okay, and if you learn logic, that actually comes from the logic part here. That's how we define intersection is and. Okay, it's and. One is called and, one is called or, but I'm not going to go to detail of that. But if you learn logic, that is how it comes from. Okay, it's or. Okay, so or this is union is or, so it took everything there, right? It's 2, 5, 4, 6. Okay, it's or. And complement is referred to the idea in logic is called not. Okay. Is say A complement is all the thing that is not there. Okay, it's not. Okay, so let's see what it is. Okay, so sample space is 1, 2, 3, 4, 5, 6. E, odd, and not same. Okay, what is E complement? E complement is the following. You go to the sample space, okay, and you kick out everything in the E. So E have 2, you kick out 2. E have 4, kick out 4. E have 6, you kick out 6. So that's why you have 1, 3, 5. Okay. So now I do the next operation here. Okay. What is the complement of L? Okay. L has 4, 5, and 6. So what we're going to do is you go to the sample space, kick out 4, 5, and 6. Left 1, 2, 3. Okay. Now to test yourself, understand, ask yourself, what is the complement of O? What's the complement of O? Complement of O is just E. Because it's not even, it's odd. Because number is either even or odd, right? Because you kick out 1, 3, 5 from the sample space, it's only 2, 4, 6, which is even. Okay, so I hope this is okay, because if you learn additional math, it's there already. If you learn math for econ like some of you, you should have learned it. Is that okay? And just complement is not, okay? Later you will understand why we want to learn this, okay? Because it's convenient to do calculation, okay? Later you will see, okay? Actually, we will use this complement thing in the rest of the semester. We always use this rule. You didn't notice, but we have to use it all the time, okay? So the idea is following. This is the sample space, right? Even has 3 numbers, 2, 4, and 6, okay? And what is not included in the even is outside, right? 1, 3, 5. So that is the idea of complement, okay? I hope this is very clear because this very simple, okay? Is there any question before I proceed? Because I hope that is clear. If that is clear, we will start to have what we call, we will have 3 different events that we will define, okay? Based on the idea of intersection and union, okay? So first thing we want to say is we have we call mutually exclusive event, okay? By the meaning, exclusive is exclude, okay? Mutually exclusive means if one happen, the other cannot, okay? So the idea is, the definition is the intersection is empty, okay? Because they can't happen at the same time. Means if one happens, the other is not, okay? But it do not say, it do allow that both of them doesn't exist, okay? So for example, as I said here is, in London or in New York are both mutually exclusive, because at this moment, if you're in New York, you cannot be in London, right? But you can be in Hong Kong, right? Or being in Hong Kong Island and Kowloon Peninsula is mutually exclusive, right? But you can be now you are in new territories, right? So it's okay. So or you are in New Asia College and in Chongqing College is mutually exclusive, right? You can't be, I mean, in the both places at the same time, right? So mutually exclusive means the intersect is empty, okay? That's the idea. Now the next thing we need to define is we call exhaustive or collective exhaustive. It means that one of the event must happen, okay? In terms of math, it means the union of them is the sample space, okay? For example, the simplest thing is being happy and being not happy are exhaustive. Must you are happy or you're not happy, right? And very often we saw this thing in the TV, right? You call when look at the sport, right? Very often in Hong Kong, sometimes they said the descriptor will say, okay, now is the penalty kick, okay? There are 2 outcomes, either you get in or you don't, okay? So when the guy who try to describe exhaustive event, basically he said nothing, right? So it's no prediction, right? Because when you try to say things like either get in or not get in, then it's empty statement, right? Because it must happen, okay? It's exhaustive, okay? So in terms of technical, is you have 2 events, they call exhaustive, then either of them must be happening, right? Because at least one of them happen, okay? Or if we have n different event and union all of them together is the sample space, we will call it collective exhaustive, but usually we ignore the term collectively, okay? So exhaustive is just like exhaust it just consume the whole thing. There's nothing left there. Okay. So it must, one thing must happen. Okay. So that's the idea, exhaustive event. Okay. So before remind you, before we have exclusive and exhaustive. Okay. So naturally you can think something we want is what we call, combine them together, we call mutually exclusive and exhaustive. In that case, we have the name we call partition. Okay. Just remind you what it means is mutually exclusive is if one happened, the other would not. Okay. But one of them will happen, right? Because of exhaustive. Okay. So that explains why this name would call partition, because you have a room, or they call sample space here. Okay. Why is it called partition? Because you're like cutting a cake. You cut it in some way. Okay. And they don't overlap. Okay. If say if this thing happened, the other will not happen, right? And they don't overlap each other. Okay. Say if you cut it in this way, okay, then you cut the sample space into different part, non-overlapping part. It must be mutually exclusive, right? Because they don't overlap, right? And they cut the sample space there, then it must one of them happen. Okay. So that's why it's called partition. Okay. And the example is you have, if you have a roll a die, head or tail partition, right? Because either head or tail. Okay. And just to remind you, the idea of partition is just mutually exclusive and exhaustive, right? So, and later you will see why we talk about partition. It is because of when you try to look at something might happen, okay? You want to partition the sample space, and then you investigate part by part. Just divide and conquer idea, right? Because look at the whole problem is very complicated. So usually what you do is to partition the samples in multiple parts. You investigate things one by one. Okay. So, but anyway, but that's the idea. Okay. Just to remind you what partition is, just like you cut out this, just like cut the cake. The samples may cut the cake. Okay. You cut it, and if one of them happened, the other would not, right? Because you cut the cake, and then there's no overlap because cut the cake. Okay. Cake cutting. That's why it's called partition. Okay. And now the example is here. We have roll a die. Okay. No, let's see the example now. We have more than 2 events. There are only 2 events. No. Say you will see the example now. Okay. So we have this 1, 2, 3, 4, 5, and 6, even number, odd number, prime number, and B. Okay, B. I don't know 4 and 6. It's a big, I think a big even number, but anyway, 4, 6. Okay, and here the first thing look at is O and B are mutually exclusive, right? Because they don't have intersection. They don't have common element. If O happen, B cannot be true. If B is true, O cannot be happen. Okay, but do note that O and B may not happen. Okay, because you can have number 2, then neither O and B is happening. Okay, and look at this. The second statement is O, P, and B are mutual collective exhaustive, because at least one of the thing would happen, because you can find 1 from O, can find 2 from P, can find 3 from O and P, can find 4 from B, can find 5 from O and P, can find 6 from S. Okay, and union them is exactly the sample space. Okay, that means that no matter you roll a die, what outcome you have, at least you can say either O or P or B happen. Okay. Now the next thing is, can we have mutually exclusive exhaustive? Yes, we have. E and O are actually mutually exclusive, right? And exhaustive because add them up is 6, right? And that means E and O is a partition. Is that okay? Is there any question? I know there's a lot of terminology there, but I really cannot skip them because we need to define probability because based on this, okay? Because we actually why we need, because we actually need mutually exclusive, okay? That is the main idea, okay? And later we will call partition, but later you see. Is that okay? Now, good. If you did I answer your question, Kwan Po? Is that okay? That's our question. Okay, maybe he's not around, but anyway. So now we learn all this operation, so we can actually define what's probability. The definition of probability, we will have 3 axioms. Okay, so you may be wonder why we call axiom. We didn't learn it. This is the way modern mathematics is being done. So everything is built from axiom, and then we derive from axiom. And axiom is something we don't try to prove, we just take it as given. Okay, and actually you learn geometry. The Euclidean geometry is starting from 5 axioms, and you build the whole everything from the geometry. Okay, so probability is like this: is we have start from some assumption, what we call axiom. We don't prove it, and then we go ahead. Okay, this is something like the principle in our life, right? We try to derive something from the very basic thing. Okay. Now, the first thing I think is very trivial. No one would object it. The first axiom is that, okay, probability is a function, okay, from event to numbers. Okay, it's like give me the event, I give the number. The first thing we say, everything must be from 0 to 1. Okay, there's no content there, but just say we limit things 0 to 1. Okay, that is the main thing. Okay, so there's nothing new there, but this is consistent with what we learned from the classical definition, right? Classical definition is a fraction, right? Because go back to very beginning. The classical definition is a ratio, right? So fraction must be from 0 to 1. Okay, so that's why when we define probability in this way, there's no loss of anything. Just saying a probability is a number between 0 to 1. Okay, we didn't say anything about 1 or 0, but just say the first thing is everything must be 0 to 1. Okay, is there any question? Nothing, just bounded. Okay, the second one we try to put it is saying that given a sample space, the probability sample space is 1. Okay, so this is also consistent with the fraction idea, right? And as I said at the beginning, when we talk about probability, the implicit assumption is we know the sample space without any issue, right? We say toss a coin is either head or tail. It can't be the case where the coin disappears or rabbit comes out. Okay, so that means that we know everything. What are the outcomes? Okay, so there's no surprise in terms of outcome. Okay, we'll be surprised that something unlikely would happen, but there's no surprise that that actual outcome would appear because we expect this possibility is there. Okay, so that's the definition of this. Okay, so this has some content. Okay, I have to emphasize this has some content there, although you may think otherwise, but it in fact imply we know all possibility. Okay, the next thing, okay, looks long, but it is saying the following. Okay, it's saying the following thing: consider an event, okay, that is a collection, just a set of mutually exclusive outcome, okay? It's just like a bunch of outcome and they cannot happen at the same time. If one happened, the other would not, okay? Just imagine A just roll a die, just A just like 1, 2, 3, okay? Or 3, 4, 5, okay? This outcome, okay? This is the last axiom, okay? This last axiom said the following, okay? The probability of this event would be the event with just the union of this, because that's what they mean, right? And we can take the union out, just sum of them, okay? Let me repeat the statement is, if the event is mutually exclusive, many outcome there, the probability of this thing will be just the sum of the probability of each outcome if they cannot happen at the same time. Okay. So the idea is the following. Okay. And even number, okay, have outcome 2, 4, and 6. Okay. And 2, 4, and 6 are mutually exclusive. Okay. The probability of even number will be the probability of getting 2 plus probability getting 4 plus probability getting 6. That is what this statement is. Okay. You may try to think this statement is very natural. Yes, it's very natural. Okay. But you may try to think what is the bite of this statement. If you want technical, which is here, is the real one is this argument extend to infinity of outcome. Okay. So this is a real bite if you want to ask, but we don't go to this detail. Is this extend to infinite? If the event have an infinite outcome, added together still the same. Okay. So this is non-trivial. Okay. This one has some bite already. Okay. But this is the main thing here. Okay. And using these 3 axioms, we can derive all the thing we want. Okay. So we have all the rules we learned from the high school. Okay. So what we are trying to do is to try to convince you they're the rules. Okay. So go back to here. Okay. I would like to try to convince you this. We can start from a definition. Okay. And try to define things. Okay. Now we have a rolling a die. We have sample space is 1 up to 6. Okay. And axiom 2 said the following. The sample space is 1. Okay. And now here comes the main thing. From axiom 3, sample space, right? We have all the outcome are mutually exclusive. So that's why you can set the sample space is summing up 1 to 6. Right? So that is the key thing here. Okay. You can separate this by probability all element here. Okay. And now what we next is have to impose, okay, is we consider a fair die. Okay. If not fair, then we have other way around, but assume the die is fair. Okay. If a fair die, then you will say the probability of each outcome is equally likely. Okay. So that's why the left hand side is 1, the right hand side is 6x. Suppose you put x there, you solve the equation 1, 6, right? Because the left hand is 1, you have a 6 of the same thing. So every one is 1, 6, right? So that's why you can assign probability for each outcome. Okay. For the same, you can assign the probability of event, right? Probability of even number consists of outcome of 2, 4, and 6, right? And they are mutually exclusive. So that's why you can add them together, 2, 4, and 6. And each one is 1, 6. So that's why it's 3 over 6, that's 1/2. So that's why we can start from the axioms and just add the assumption that every outcome is equally likely, then we can derive everything. Okay. So that is how we start with the axioms. Okay. We don't have to rely on the idea that we roll a die many times what happened. Okay, there's nothing about real world. We just say, okay, these are the outcomes. Okay, and then we tell them how outcome are related. We make assumption, and then we can derive probability. Okay, so that's nothing about real world. So that's why it's consistent with what we call belief or computer simulation. Okay, as long as you make some assumption, the probability will what it means. Okay. Now, is that okay? As I said, the real bite of axiom phi in the modern mathematics is to extend to infinite sequence, but I guess it's too much to talk about this in our class. But just remind you, if you learn, that it will be a very complicated thing there. Okay, but I think it's fine. No, we don't talk about the infinite stuff. Okay. Now, the next thing is, this is what you learn in the high school, complement rule. Okay, and we try to say the complement rule can be derived from axiom 2 and axiom 3. Okay, do note that A and A complement are mutually exclusive and exhaustive, right? A and its complement must be mutually exclusive, right? Because that's what the complement means, and they are exhaustive. So A and A complement actually is a partition, right? And it must be the probability of the maybe can I write here? No, the proof is very simple, right? Because probability of the sample space is 1. Okay, a sample space is indeed A union A complement, right? And because they are mutually exclusive, you can write it, right? A. Okay, and just move one to the other side. That is, I mean, I don't do the proof, but this is how you get that statement. Okay, I mean, you don't need to care about the proof, but it's very obvious, right? You put it to the other side, right? A plus A complement must be equal to sample space, which is 1. Okay. So, so why we know this from the high school, and some of you would have remembered it, but let's look at the example here. Okay. So this is very convenient when you calculate complicated probability. Okay. Say, for example, if you try to ask a question, now for that is simple. What is the probability that the face value is less than 6? Okay. And you have to count the die 6, you'll be 5, 4, 3, 2, 1. You have to count 5, right? But the other way around is look at the complement, low less than 6. Okay. But in that case, only one outcome, right? So that's why A complement is 1 minus 1 minus 1 over 6. Okay, which is 5 over 6. Okay. Is that okay? So the idea is like this, okay? We know the 6 outcome, okay? We know the complement is 6 is here, right? So we just calculate the probability of this guy, and 1 minus this guy, you get the answer. Okay. So should I cover this one? Okay, maybe I cover this one a little bit. Just technical, in case you want to know, that would be good. Okay, so this is something like the following. In case you want to know, then you can take a rest. In case we have a partition, right? Partition means that mutually exclusive and correlative exhaustive, right? So the sample size, right? Because mutually exclusive, we add them all up to 1. Okay. And in that case, it's useful to look at this problem. Okay. Look at the roll the die twice. Okay. What is the probability that the sum of two row is less than 11. Okay, so to calculate this is a difficult task, right? Because we have 36 outcome, right? So you have to calculate all possibilities less than 11, right? But you do look at actually you have consider the following. Okay, you do the partition. Okay, AI is the event that the sum of the result is I. Okay, and you know you can partition the sample space to A2 up to A12 because it must be minimum is 2 up to 12, right? You cannot have 1, right? Because 1 is 2, right? If the maximum is 12, it's 6 to 6. Okay, then you can calculate what is A11. A11 only have 2 outcomes, is 5 and 6 and 6 and 5, right? So that's why 2 over 36. And A12 only have 1 possible, is 6 and 6. So that's why it's 1 over 6. Okay, so that's why these two are mutually exclusive, right? So that's why and asking you from 2 up to 10, which is the question asking, right? The same as 1 minus 11 and 12, right? So this is complement rule, right? And 1 minus 3 over 36 is 11 over 12. So that's how you can calculate this very fast. Okay, and do remind you that because we are not math class, so we are not interested in asking you that complicated thing. Okay, just putting there in case you want to know, and some of you actually learned it in the high school already. So just put there to let you understand what's going on. So I have a gray color here, so don't worry, it's not going to be something that I deliberately ask. Okay, so I hope that is so. Don't feel worry if you think this is complicated. I will ask in the exam. No, I mean just to let you know that it is something in the gray color. Okay. So this last rule I want to talk about today. Okay, there are many implications about the axioms. This one we call addition rule. Okay, we will learn more rules. Say later we learn total probability rule, propagation rule, odds ratio, condition probability, many things. But we just end up today. We want to finish this. It's called addition rule. Okay. The addition rule today we want to talk about is try to tell you how union or interset are related. Okay. And in set theory, sometimes people call inclusion exclusion principle, but in probability is called the addition rule. Okay, so what here is the interset same as the A plus B minus A union B, or A union B plus A plus B minus A intercept B. Okay, so you just swap the two, you get this guy. Okay, you just swap these two, just use equation, you get this one. Okay, now we can prove it. Okay, and but we are not math class, so we're trying to justify why this is correct using graphics. Okay, so let me draw a diagram to convince you this is correct. Okay, this is A. Okay, and this is B. Okay, and you can tell me, right, this is A union B, right? And you would tell me this small guy will be A intercept B. Okay, if you try to draw this, is A intercept B, right? Intercept B is here. Okay, so look at this simple geometry idea. You have a blue area, blue color, and a red color thing. Okay, and you add together, you double count the orange color, right? So you have blue plus red minus orange is purple. Okay, let me repeat. Purple is blue plus red minus orange. Repeat. Purple, blue plus red minus orange. Okay. Now go back to the slide. Okay. This purple, right, is red, blue minus orange. Okay. So this is what it means. Okay. So I guess I should end this with the example. Okay. And then we'll continue next class for the rest. Okay. Addition rule. Okay. Asking the question is, you roll the die once, what's the probability of having an even number or a number greater than 3? Okay. So to do it, you will say A is the even number and B is greater than 3. Okay. And even number is just 2, 4, and 6, right? And greater than 3 is just 3, 4, 5, and 6. Okay. And what is A and B, right? Is they are even number greater than 3, okay? Or A intersect B, right? So you just find a common element, which has 4 and 6. That is the intersect here, okay? So the question is asking what is A union B, okay? A union B, okay? And now let's see how you do the calculation, okay? A union B is just 2, 4, 5, and 6 because you pick up everything there, okay? So we just 4 outcome over 6 outcome is 2/3, okay? And this is direct calculation, okay? So the question is, what if we don't do direct calculation, okay? We can find A is 3/6 because 3 outcome here, okay? B is 3/6 because also 3 outcome here, okay? A intersect B will be 2/6 because we have 2 outcome, okay? So therefore A union B will be A, okay, here, plus B, which is here, minus A intersect B, give you the final answer, okay? So give you 2/3, which is the same, okay? So I guess I should end now. I will see you next week. Tomorrow we have optional tutorial. You may want to join, but I will see you next week. Bye bye. Thank you.